For those of us in production engineering, we kind of thought releases were a solved problem, right? Well, it turns out we were wrong. Today, we're going to dive deep into why generative AI is fundamentally breaking our most trusted deployment models. We're going to explore a completely new mindset and a system for releasing intelligence safely. Because when you start shipping systems that are probabilistic, the old rules don't just bend, they completely shatter.
I love this quote because it just gets right to the heart of it. We all know blue-green deployments, you just flip the router from the old stable thing to the new shiny thing. It's clean, it's predictable, but you can't do that with intelligence. An AI model is, by its very nature, unpredictable. It's probabilistic, and that means releasing it requires a totally different way of thinking.
So here's our plan. First, we'll talk about why Gen AI just doesn't fit our old models. Then, we'll look at why something like a canary release is actually a recipe for disaster here. After that, we'll start building up the solution. How to observe with zero risk, what to compare, how to build a safety net, and finally, how this all comes together into a brand new philosophy for releases. Okay, let's jump right in. The core of the problem, really, is this massive collision. You've got the fluid, probabilistic world of AI, smashing right into the rigid, deterministic world that we built all of classic software engineering on. They just don't speak the same language. And this slide really lays it all out. For decades, our entire world was built on a simple, stable truth. If you put the same input in, you get the same output out. Every single time. Our tests, our monitoring, our own sanity, it all relied on this. But Gen AI, it completely violates that stable truth. It's designed to be probabilistic, and that means every single tool and process we built on that old assumption is now a potential point of failure.
So this brings us to pretty much everyone's favorite safety net, the canary release. This has been the gold standard for rolling out new code safely for years. But we're about to see why this trusted technique isn't just a little bit flawed for Gen AI. It's actually dangerously ineffective.
You know the drill, right? The classic canary logic is so simple and elegant. You send a tiny fraction of your users, maybe 10%, over to the new version. The other 90% stays safe on the old, stable one. And you just sit back and compare basic stuff, like error rates. If the new one looks okay, you just slowly dial up the traffic.
Well, this is exactly where it all falls apart with AI. First of all, what even is an error rate for language? A response isn't a 500 server error. It could just be subtly wrong or weirdly toned or just off. On top of that, users are smart. They change their prompts based on what the AI says, which completely messes up any clean A/B test. But here's the real killer. One single bad, brand-damaging response can destroy a user's trust forever. By the time your aggregate metrics even start to twitch, the damage is already done.
So if we can't even expose 1% of our users to a new model, what are we supposed to do? This is where we have to start thinking differently. We need a way to see how the new model behaves in the real world, but with absolutely zero impact on our users. And that brings us to the core technique, shadow traffic.
The idea here is simple, but it is so powerful. Instead of routing a user's request to the new version, you mirror it. You make a copy. So the original request goes to your current live model, and the user gets that response, completely unaware that anything is different. At the exact same time, that mirrored request goes to your new shadow model. And its response, it doesn't go to the user. It just gets logged for us to analyze. The results? Zero user risk. And here's the architecture, plain and simple. You've got the live path, that's high risk. Anything that breaks there, the user feels it. Then you have the shadow path. The user's completely isolated from it. The response is just for us, for our logs. User risk goes from high to zero. For any serious Gen AI system, this isn't some optional pattern anymore. This has to be the default. Okay, so we're safely shadowing our live traffic. We're getting responses from the new model without hurting anyone. That's great. But what are we comparing? Just doing a text diff between two responses is totally useless. We have to go deeper. We need to start comparing the behavioral traits of the two models. This is where we stop acting like we're comparing text files and start acting like systems engineers. We need to define the vital signs for our AI. We're measuring stuff like, is it hallucinating more? Is it violating our safety policies? Is it calling tools correctly? Is it overconfident or underconfident? These are the real metrics of an AI's health. And here's what that looks like in the real world. This is a behavioral diff. Our live model is humming along with a hallucination rate of 0.6%. But look at the shadow model. It's at 1.9%. That is a huge jump. And at the same time, its average confidence has dropped significantly.
Now, this is concrete, actionable data that we can use to make a decision.
But of course, data is just noise until you apply rules to it. So as engineers, we define clear, unambiguous divergence thresholds. We can say a hallucination rate over 2% is an automatic failure, or a drop in confidence of more than 0.1 is a major red flag. And for something like a policy violation, that has to be 0, period. These become our automated guardrails.
And here is such a critical part of the process. When one of these thresholds is breached, we don't just automatically shut things down. The first step is to alert. You page a human, you get an engineer to look at the data and investigate. The whole point is to empower engineers with amazing data, not to take them out of the loop.
Now let's say we do all our testing, we promote the model to live, and something still goes wrong. An alert isn't enough in that case. We need an escape hatch. We need a way to get back to the last known good state, and we need to do it almost instantly. Let me be clear. Speed here isn't a feature. It is the safety system. This is a massive distinction that anyone running large-scale systems will appreciate. A rollback in this new world is not a slow, painful, 10-minute-long redeployment. No way. It is a pointer flip. It should be as fast and as simple as changing a single line in a config file. I mean, look how simple this is. Your whole system is just reading a pointer somewhere to figure out which model version to use. If the new version, 3.1, starts acting up, the rollback is literally just flipping that pointer back to the last stable version, 3.0, and that's it. The fire is out.
So for this to actually work in a crisis, your rollback system needs to have these 3 properties. It has to be config-driven, not code-driven. It has to be safe to do at runtime without restarting anything. And it absolutely has to execute in milliseconds. If your rollback takes minutes, it's already too late. So let's just pull this all together. What we've been talking about, shadow traffic, behavioral diffs, instant rollbacks, this isn't some abstract AI theory. This is pure, hardcore production engineering, just applied to a totally new kind of probabilistic system.
And this whole system, it doesn't live in a vacuum. It's just one critical stage in a much bigger, mature MLOps pipeline. You see it right there at step 4. And the quality of this stage depends entirely on the steps before it, like defining your artifacts and running evaluations. And all the steps that come after it, like policy enforcement, depend on this stage being done correctly. It's all connected. If you only remember one thing from this whole explainer, please let it be this. We have to change our language, which will change our mindset. You don't deploy a new AI model. You release it into a safe, monitored shadow environment, and you watch it until its behavior proves that it has earned the right to be promoted to production. So I'm going to leave you with this one question to take back to your teams. Right now, if your live model started going haywire, could you roll back to a known good state in milliseconds? If the answer is no, you're not just running a risk. You're basically shipping untested intelligence and hoping for the best. It's time to rethink your release philosophy.